Hi. So it's my pleasure to welcome Bianca Zadrozny. Bianca Zadrozny is a research manager at IBM Research Brazil, leading the Natural Resources Analytic Group. The group's mission is to conduct research projects in data-driven analytics for decision-making in the areas of oil and gas and mining, with a great focus on developing new machine learning workflows to aid geoscientists in the discovery of natural resources. Bianca got her PhD in computer science from the University of California, San Diego in 2003. After that, she has worked as a researcher at IBM Watson Research Center, New York, and as a professor at Federal Fluminense University in Brazil. Then she joined IBM in 2011. So, welcome, Bianca. Thank you.
Thank you, Pablo. I'm very glad to be here. It's my first time in Uruguay, even though I live in Brazil, which is a neighbor country, and I'm very happy to see this event, very nice event, happening here in South America. So it's a great pleasure indeed, and thank you very much, Pablo and Meire, for having me, invited me here. So the topic of my talk today is machine learning for subsurface characterization. And I'll start just by telling you a little bit about IBM Research and IBM Research Brazil, and then dive into the topic. So basically, IBM Research is a global research capability, and it has existed for over 70 years in many countries. Of course, it started in New York, where we have the T.J. Watson Research Center, and we also have big centers in Zurich and across the world. Our newest lab is the one in Africa, which is about, I guess, 6 or 7 years old. But the one in Brazil, it was started in 2010. And I joined the lab in beginning of 2011. We have facilities both in Rio and in São Paulo. In Rio, I was the first researcher to join the lab in Rio, so I'm very proud of that. I'm very happy that company decided to create a research lab in Brazil, right? Because when I went to school in Brazil, there are no research labs in computer science related to companies there, and we saw that happen, and I was able to participate. So, like I said, we have labs in São Paulo and Rio, and we have this focus on natural resources, which I guess some people could find a little misleading, this name, especially after the talks on AI for social good. And I have to say that I feel a little bit pressure in the sense of presenting this topic and the work that we do because of the oil and gas related mining and people feeling this is a bad thing. But I personally think it's a good thing, and if you want, I can talk about this afterwards, but I don't want to make this the topic, the subject of my talk. But I'll just say that the fact that we do research in this topic is driven by the fact that Brazil has a pre-salt and was discovered in 2010, and a lot of companies actually went and invested in Brazil, included IBM, because of this reason, because part of the money that goes from the oil and gas exploration has to be invested back in research, and we do take advantage of that to create the lab, and we develop partnerships with oil and gas companies to do that. And I think that's actually a good social thing, because we are able to create a lab in Brazil and have people working there as part of this, and we all need the energy to travel, like for instance, to come here by airplane. There's no way anyone can travel without oil and gas, and there's no technology in the near future, as I can see, for planes to fly without that. So, okay, I said I was not going to say anything. I said something, so I don't feel so bad about it, but okay. So basically, we have AI, and we also have nanotechnology lab. We have some researchers that came from the Yorktown lab, and they're developing, they're studying the flow of oil and water in very small to actually understand how we could actually extract more oil from the rocks from the same place that you already drilled, right? So this is a big interest because you don't have to explore new places. You can just inject nanoparticles and get more oil out of the same places. So anyway, I'm from the AI side. I talked about the two sides that we have there in the area of oil and gas. So another interesting thing why I think this research area is really cool and I like to work in it is that we have this AI for natural resources industry approach where we try to combine AI technologies with something that we call practice and context understanding, which is studying how the experts, the geoscientists, they make the decisions and how the tools could help them. So we do more in the sense of augmented intelligence than just artificial intelligence algorithms. We want to understand how they can actually put knowledge into the tools and also to understand what they get out of it. And for that, we work together with HCI researchers in this area. And we also try to connect with the data-driven side, which is my side. I came from a machine learning background, so my group works mainly on this side of AI technologies for vision data-driven models, and that's what I'm going to present more today. But we also have a group working in this fit-for-purpose knowledge engineering, which is the construction, adaptation, evolution of domain ontologies, and how to actually put together knowledge with images and these hyper-knowledge techniques that we have there. And when we put those three things together, we create projects that are not just saying, okay, I ran this machine learning technique, I got this result, etc. But it's more like how to use the machine learning techniques in the context of an expert that is making decisions and things like that. And for that, we take into account many different areas of AI that are not just machine learning. But as I said, my focus and the focus of my group is more in the side of machine learning, and so most of the talk would be about that. So what is subsurface characterization? So basically, there are different areas in geophysics where and geology, etc., that you take direct and indirect measurements from the physical properties of the subsurface of the Earth, like seismic surveys, well logs, core samples that are parts of rock that you take from, you drill and you take the rock and you analyze that. And there are whole schools of people that are the exploration geologists, etc., that study these data sources, considering their geophysical and geological knowledge to create models of the subsurface of the Earth that then they can use for different tasks to say, for example, oh, okay, is it worth it or not to buy this block in Brazil to build a platform there, for example, right? So very high-level decisions in the biggest oil and gas companies, they rely on many different data analysis done over time by different people, and then they get to the point of saying, okay, I want to make a decision, for example, to acquire this place. So seismic surveys, they are similar in some sense to ultrasound, in the sense that it's an indirect measurement that you take from waves that you generate somehow, in this case through could be micro earthquakes, and then you get the results and you reconstruct that. That's actually a process called seismic processing that you have to do inverse analysis to reconstruct what would be the image underneath the Earth, the same way that an ultrasound works. So this is one of the main sources of data in the case of oil and gas. An interesting fact, for example, is this image. The resolution is really low if you consider that, for example, this size here is about 1 kilometer, this small thing here, right? So the seismic surveys are very big surveys, and the resolutions, like 1 pixel, is like meters that you have. On the other hand, you also have the well logs, which are basically when you drill, you send a sensor down, and the sensor will acquire some information that can be different kinds of sensors, different physical properties that you acquire around the place where the well is drilled, right? So usually there's some exploration well, so a company will go there and build a well, and when it builds the well, it will get some data out of it to actually understand what are the layers of rock in there, etc. And the same thing for mining as well, like you could do this to understand the layers of rock inside the earth. So, but in some cases, for example, you only have seismic data, could only have well log data, depending on the situation, right? Depending on the kind of field that you have and the history of the field, etc. So basically, what is like machine learning for subsurface characterization? It goes back some long way if you think that, for example, geostatistics is a field that focused on the analysis of geospatial data sets. It started in the 60s because of the need to try to predict gold, or based on distribution of different places where they found, and then they interpolate that. So some of the spatial interpolation methods that now can be mapped into Gaussian processes, they actually go back to this time. And the traditional signal processing and image processing, classification techniques, etc., also have been in use by the industry for years, like to correlate data and to make predictions, etc., based on this kind of data. But nowadays, since this big change in machine learning, the new algorithms that are a lot successful for image analysis, for example, or for natural language processing, as all the industry saying, okay, you know, can we develop or apply the same kinds of techniques for problems in this domain, right? So basically, what we started, when I started in the lab, let's say around 2012, 2013, I did some work in deep learning for natural language processing, some work on character level embedding, things like that. So I had some experience in this area, and I started seeing all the image things happening. And we said, okay, let's think about, and for me, this was like, wow, this would be a big dream that you can apply deep learning to seismic images. It wasn't something that was being done already. So for me, it was, wow, I have to like hire people and get some things going. So this is not something that it looks easy when you look now, but at the time and how we started, it is not. And nowadays, yeah, people are doing this, and us and others, so I'm mentioning ones that and if you go to a geophysics conference nowadays, you'll see a lot of work in deep learning and applications and workshops in that. So it's really changing that field. So I think also it's important for artificial intelligence people to know about that, even if some people may not like the oil and gas industry, your algorithms are working for them as well. So the machine learning for subsurface characterization. So one of the first things that we did work, and it worked quite well, is this actually trying to predict layers based on the seismic data, predict the different kinds of layers of rocks. So this is using semantic segmentation kind of networks. We can apply that to segment the seismic images as well. We also have work in interpolating seismic image. We have one that it's related to a data set, a benchmark that we have created using seismic data sets that we hired people to interpret for us and release that as a data set that other people can use to develop things. There is this paper that we did on mining, on the use of 3D convolutional neural networks for our content estimation that is actually quite new in the sense that no one had used this kind of convolutional network for the spatial interpolation problems. And the super resolution deep generative networks for seismic data. So I'll go a little bit into more detail about the generative networks work and present some of the results. So basically, we have the seismic data. It can be either a marine survey or a land survey. And what we get as result after the seismic processing is this seismic cube. And from the seismic cube, we generate we have slices that are seismic images. They're the cross lines and inlines that have to be processed. So for example, in the one that we did semantic segmentation, we trained the network on a few of those slices, and then we use it for all the other slices, so saves a lot of time of the interpreter that is doing that. But in the case of the conditional GANs, or the GANs that we use, we actually tried them for 2 different applications. One is the seismic resolution improvement, and the other one is generate synthetic seismic images from simple sketches. So going to the conditional GANs in work, a lot of people know this right here. This was proposed by Goodfellow et al., and I also have more recent by Isola and all. And we are using here just a general purpose solution to image translation. So the idea is that these networks, because they're trained adversarially, they learn also the loss function to train the mapping. So it's a lot of people, I guess, already know about this, but we do have a generator network that takes an image and generates another image, and a detector network that tries to decide whether or not this is a fake or the real image. So we used, in this case, the pix-to-pix architecture, where the generator architecture is the UNet, and the discriminator architecture is patch-GAN. And the data sets, it was a public data set called the Netherlands F3 data set, coming from Netherlands, and this is the number of inlines and cross lines, which are those slices for the seismic cube. And the area that it's covered is 24 by 16 kilometers. So the idea here is to say, there are 2 cases that I said we are going to cover, right? The resolution improvement and the generating synthetic seismic from simple sketches. So in the case of resolution improvement, in many cases, having this dense and regularly sampled data set is very important for many seismic processing data sets and interpretations. Once you interpret it, go to next step of getting the models, getting the geological models running. So we want to see if we are able to increase the vertical and horizontal resolution of the seismic data using GANs. And this work has been published in a journal paper in this Geoscience and Remote Sensing Letters. Right? It's improving seismic data resolution with deep generative networks. So basically, in the case of the resolution improvement, when the generator receives the low resolution images and synthesizes the high resolution image, the discriminator receives a pair of images and decides whether it's real or fake. Right, so the generator is trying to beat the discriminator to generate better and better images. So in this case, we train we separate the training and test the data in tiles of 256 by 256 pixels. So because you cannot feed, like, say, a whole slice into into a network, right? It would be too big for the network to process. So we have to break the image into smaller tiles. So this is a processing that we always have to do in most of the machine learning algorithms in this area. We have to do this tiling before we apply anything. And we train the network with regular learning approaches. And we evaluate using different metrics. In this case, we are using metrics that compare the produced image with the real image. In this case, we are using data that we have introduced the noise, and we are checking whether or not we get the resolution improvement. So here's some comparison. Hello? Oops, sorry. Yeah, here is some comparisons of the cross-line dissimilarities for GANs and for another approach, which is the cubic interpolation, and the results are quite amazing in terms of the difference in performance by up to 72% of the traditional cubic interpolation across many different settings that we tried in terms of experiments. And if you look at the results, also it's very amazing that visually you can see that there is no comparison. So the seismic sketch was another idea that one of the researchers that worked with us, he knew that the geoscientists, they like to sketch what this Earth subsurface looks like, so they will draw, let's say, different layers, and based on that, they will talk to one another and say, okay, I think it looks like that, so if it looks like that, it might be this, because this subject is highly subjective. In order to interpret a seismic image, you have to understand all the geological history of that area to know what are the possibilities. It's not like I see the image, I know exactly what is there, like a regular image, right? So one of the ways they communicate and they share ideas and they look at possible things to do is to do the sketches. And so to communicate to peers for educational purposes, etc. But also, we can also think about other uses when they sketch. If you can transform that into a regular seismic image, you can actually go and look for that pattern in the database, right? So if they say, okay, I'm looking for this particular pattern, they sketch, then you can do that. So, of course, GAN had been used already for this kind of thing in other situations that people sketch. But for other things, let's say shoe, you don't need to sketch if you can describe things more or less. Not everyone will know how to draw a shoe to search, right? But in this case, for the geoscientists, it made sense, right? They have this way of drawing and communicating from them. So, and the other one is to augment machine learning training data sets. So if we want to create more cases that we haven't seen and we want to be able to train on that, then we can generate that to train for another task also. We haven't done that already, but that's theoretically is another possibility. So again, we use the same kind of network, but in this case, instead of feeding it a lower resolution, higher resolution image, we feed a sketch and what would be the seismic for that sketch. So to train, we ask someone to go in the opposite direction, take a seismic image and sketch what would be that seismic image. And then we go in the forward direction to, given a sketch, be able to generate the seismic images. So again, it's a similar process of training and test. We take some part of the cube for training and another part for testing. And we also divide the data into smaller tiles to be able to train the GANs. And when we do the seismic sketches, we were deciding, what would be the good kind of sketch that people could do, and also that the network would be able to predict well what would be the seismic image for that sketch. So we tried different kinds of sketches that they could do for one original one. And some of them we created using Canny edge detector to find some edges and then take that into, for example, the first one there is automatically created by using edge detector. And the layers plus the edge, and then layers plus colorful edges. So different possible sketches. And again, we train the network using some specific parameters. We will train one model for each sketch type. And like I said, we use the Canny edge detector from SideKit image to generate sketches with different levels of accuracy in terms of following the edges. We use the interpretation of 9 horizons from the Penobscot dataset that we have interpreted. So we take already to do the sketches, we take the layers that have already been done by the geoscientists. And we compare the results using different metrics of image comparison. And again, here we see the numbers of comparisons between the different kinds of sketches and the original image. So you see that for some cases, sketch D was better. For some cases, sketch E was better. In terms of the, for some metrics, sketch E was better, and for some other metrics, sketch D was better. And here is for the metric DSIM, you see the box plot showing the variance here in terms of the results. So it was kind of clear that having so if you look at what were the sketch types, having the layers with either black edges or colorful edges was better than having either colorful edges or just the layers. So having both of them helps. So people need to draw like that. And believe me, the experts, they know how to interpret these little lines, and they come up with explanations for them. So for us, it doesn't look like something possible, but for them, it's very interesting. We made a tool, and they started drawing. They're very happy to draw and see the actual results coming out. For them, it's like really exciting to be able to do that. So going back, here is some other examples that we try more challenging situations where, like, some of the layers, they go over each other. And you also, here if you look, this is the original image, and here is the output, right? So clearly, like, for instance, the one that doesn't have the edges here, it's missing some of the patterns that are important here. Okay, so I'll talk now about a different project that it's called Sweet Spot Finder for Shale. This project we actually developed in partnership with Shell. And in this case, we are working only with well logs. So it's a kind of field where you don't have any kind of seismic survey, because they're focused on one specific layer that they already know a lot about. They already have lots of wells that have been drilled there. And they're trying to optimize things like, where do I put my next well in this field, right? A field that already has been explored, and we are deciding this new thing. So in this case, we actually have, besides the petrophysical measurements and the geological interpretations, we also have well completion parameters, which is related to the engineering of the well. They also impact on the actual production. And the goal of the project was to build a machine learning model to predict the total production of a new well in a new location in the same field where we already have all the other wells. So what we had to develop in this case was something that first, what we call a petrophysical feature map generator. This takes different kinds of well logs, horizontal well logs and vertical well logs, and interpolates them spatially. Here we use spatial interpolation methods from the literature, kriging, etc., that the geologists work with. Lately, we have been working also with other kinds of spatial interpolation. But in general, what this is doing is taking data that is over a field and making it available everywhere in the field, right? Because you only have data in the points where you actually have drilled and you have censored with the well log, and you want to be able to predict for the whole field. So we have to do this feature map generator. Then, with the completions and engineering data, these are actually parameters that control the production. And our goal is to actually separate what is the effect from these parameters, which are geological, they are inherent from the Earth, versus this one, which is something that they have to make a decision on, like how long should my well be, how much should I inject. So they have to make all these decisions to predict the well production data. So what we have done is to try different approaches in terms of what are the machine learning models that we use to, given all this data, predict the production, so that we can do an effect analysis afterwards and say, for example, if I increase the number of the length of this well, how much more is it going to produce? And one thing that we have here is this machine learning with domain knowledge constraints, because in this case, there are some physical constraints regarding the model. And as I said in the beginning, we work with knowledge engineering as well. So we put together, based on the knowledge engineering, what are things that should not happen. For example, as I increase my well, I know that the production is going to go up. And things like that. So we put those as constraints into the machine learning model, especially because in this case, we don't have a lot of data, right? The data set is in order of hundreds of wells. So it's not like we can build a model just using only data that, because we have a lot of data, we can train like that. So, and the last step is to separate what is the effect from the production, for the engineering parameters on the production, from the effect of the location. So we create a heat map of the locations that are better versus, and also the effects of the different engineering parameters that are part of that. So in this methodology, we test that in one specific basin, where we have some 74 horizontal wells, 264 vertical wells, and we have production for 152 producing horizontal wells. And these results actually have been published in petroleum engineering conferences and journals. Sorry. So basically what we compared was, is it better to use black box machine learning models, any one that you can get from standard tools, and we run any of them, all of them, versus using some model that it's called generalized additive model, where you actually fit a function that it's a linear function of splines, where each of the splines is one of the features in the model, and the XY actually is a combined spline, right? So there is one spline that is actually related to the location of the well. So in this case, and we model the log of the production. So this, in some sense, it's a model where you do put in some knowledge, because you say, like, okay, what are the factors that they can be linear correlation, but there is the splines that you can fit and be very flexible with them as well. So these are the generalized additive models that are very much used in statistics. So when you have small data sets, those kinds of models are actually very helpful. And shape-constrained additive models is the same thing, but you can actually put some constraints on the shape of the function. So you can say, for example, I know this function is monotonically increasing. I know this function is monotonically decreasing. And this, by the way, you use from R, but you also, we found some libraries in Python that someone had done open source. And then we contacted them, and then they changed the license so that we could use within IBM as well. So that's an open, there is the implementation of these models. They are available. They were done not by us, by other people. They're gave very good results for this kind of model that we are doing here. So here I'm comparing GAM with random forest, SVM linear models. And this we were testing whether or not to, this was another issue that we're testing, whether or not to use gamma ray only from the vertical wells, no gamma ray, or gamma ray from the horizontal wells. And this was an issue for the Shell people. They said, okay, we never showed that using well log from horizontal wells can actually improve the prediction of a model. So if we can show that, that's very big. But actually, the difference between the GR, no GR and GR vertical is small, or the effect of this gamma ray, which is one of the well logs on the production, is not that big. And when you change a little bit, you know, if you use only the vertical or the horizontal, it's not that big. But it did improve somewhat using both the horizontal and the vertical. And this CAM, which is the shape constraint additive model, actually gave the best result here, which is the one for which we impose the domain constraints. And if you look at the graphs of the nice thing about the GAMs is that they generate those effect graphs. So you can actually look at the effect of each of the variables on the production. You can also look at the effect of the locations on the production. And they look like, in this case, for example, this was one of the things that when we showed to the people in Shell, they were like, no way, this is like really wrong. When you increase the length of the well, it should not go down like this. And the reason is that we have very few data points in this region. So here the model is very noisy, and it thinks that there's only few data points, so somehow it's seeing some spurious correlation and saying, okay, this should go down, for example. So it's another variable that we're not seeing that it's influencing in the model. I watched the talk yesterday about causality. Unfortunately, we cannot interfere very much with the experiments here to generate data sets to infer the causality, but we can look at the effects and talk to the experts and use their causality to improve our models, so that's good. And hopefully not just talk, but embed the knowledge in a knowledge base and use that for other people as well. So here the same thing with the gamma ray, it's like this, but there's also this shut-in days, which is the number of the days the wells are shut. It goes down a little bit. It goes up a little bit here and then goes down. This is very small, but still it is not correct. So when we use the shape constraint, of course, it's forced to do that. So it will be like this, and it will be like this here. So for them, it's much more, makes a lot more sense to look at these graphs than look at ones that are not make sense physically for them. So I'm almost done. So I'm going to talk a bit about what's next and what I see for my group in terms of research directions. So we'll keep working at least for 1 or 2 or 3 more years, 4, I don't know, in this area, because there's a lot of interest, there's a lot of new things, interesting things that we can do. Specifically, we are thinking, there are a lot of geodata scientists, people that they do analysis of those data sets in the oil companies, and they need to accelerate the development of machine learning models for the subsurface. Right now, it's like the researchers in the companies, we talk to them and they are applying, they're trying different things, but it's not something that all the geoscientists, they don't have to have a lot of expertise in machine learning to be able to start building those models. So a vision that we have is that we have to create like a tool that facilitates the creation of machine learning models based on reading the industry data formats, doing the data preparation, suggesting possible architectures, things like that. And they can, and this kind of framework actually applies to other domains as well, but in this case, we know already the domain very well, and we know that people need this kind of formats and transformations and things like that in order to apply the models. So we are working on that, and we're seeing how we're going to make this available to other people. We are also working on novel spatial model evaluation and transfer learning methods. So we are basically, this is an area that I did some work in on sample selection bias. I have some papers back from 2001, 2000 that you can look up if you wish, and also some work on calibration, things like that, more pure machine learning. We are revisiting that and looking at this in the case of covariate shift, which is an area that developed a lot, looking at this in the sense of the spatial data. So when we train a model in one region, if you can how do you transfer to another region, take into account the knowledge that you have about, okay, this is a similar geology, etc. And then basically my goal is that I can take all the different data sets from different fields anywhere, and I can automatically decide, does it make sense to put does it make sense to put the data sets together and learn a single model? Should I separate in 2? Does it improve or not the results? And now we hired the person that did a PhD in Stanford, the Brazilian guy that worked in geostatistics, did a PhD there in Stanford, and he moved back to Brazil. I don't know the reason. I think he liked Brazil a lot. But he is very passionate into this, and I'm very happy that we are going to start working more, and I hope we'll be able to do some cool research on this stuff. And the solving problems in subsurface characterization using developing this RockML library that we have been developing. So we have other researchers that are more into taking, like the work that I showed about the GANs, taking other problems in the industry. There is velocity analysis, noise attenuation, horizon peaking, well log prediction, facies formations, predictions. There are many other problems in the industry that you can apply those things and actually see what are the best approaches, etc., so that we can incorporate that into our library. And to finish, I'd just like to comment that in general in the lab, we have this view now, and this goes together with, like I said, we have some knowledge engineering people, some software engineering people, and me as some other people in machine learning. And we are thinking more about this knowledge augmented AI and ML. A lot of people have been thinking about explainability, about how to embed domain knowledge. So we are trying different approaches, reading literature in neurosymbolic, thinking about that as well, because in this area, it is really important to, like I showed, for example, embed domain knowledge as constraints for the machine learning algorithm. There's also a group that is a sister group of mine that is working on physically informed neural networks for simulation. So those are networks that you can model differential equations. And in cases where you have some data but not a lot of data, you can use both in the physically informed neural networks. So they have a challenge now in IBM Research related to the use of this for simulation. In general, we use models trained in different areas with similar geology. Like I said, this is my goal of being able to tell whether or not I can reuse or not a model. And then there's work with the people in the knowledge engineering of when we do label images, we can do some reasoning in terms of, saying spatial reasoning in terms of what has been found based on the previous knowledge, for example, that in certain regions, this is a salt dye appear only if there is a minim basin around and things like that. So there is some contextual reasoning that has to be done here to actually find bigger pattern in the seismic images. And also, like I said, neurosymbolic could also be one approach here that we're trying to use, but it doesn't work very well in practice. That when you put try to embed some domain, use logic in neural networks and things like that, they do not scale. So right now we are using these two separate approaches. We do use the neural part to extract low-level features and the high-level part to do reasoning on top of that as well. Finalize, like I said in the beginning, there's a lot of activity in the exploration geophysicist area in terms of machine learning. They actually had a workshop in Rio 2 years ago, and again, they're going to have a workshop in Rio in May. This was just announced, and there's a call for papers for December. I don't know if other people here probably. Not a lot of people work in this area, but I just wanted to mention so you know that machine learning and geophysics is a really hot topic now. Yeah, I just want to thank you, and I want to say thank you very much to all these other people that work with me in the Brazil Research Lab. Okay, thank you.
Thanks, Bianca. Thanks a lot for your talk. Do you have questions? We have time for a couple of questions.
I don't know if the terms are the correct here. I don't know if the terms are the correct one, but when you drill, when you are looking for a new place to drill a well, does the production of that well, will it affect the production of the others?
Yes.
So how do you solve this?
This is a problem. So you got a very good point. In this case, we are assuming that there is some distance from the well, and those are shale wells. So it doesn't affect very much because the fracking and all of that related to shale is because you have to fracture the rock in order for the oil to flow. So it doesn't flow very far away from where you put the well. So it doesn't interfere that much, but there is a minimum distance that you have to put. So yeah, this would be something that is like a post-processing step. We don't optimize for that in the sense of saying, okay, I want to find the one that is not really close to anyone, although you could. So actually, we don't do any optimization here, and we assume that the production is like the sizes are, the wells are far apart in the sense that they are not going to interfere. And we also don't do the optimization step of choosing the actual location because that depends on other things that they take into account in order to do that. So they only take the production estimate into account from the geology and the spatial and the data around the point and things like that. But it doesn't interfere. It's more like mining than other oil and gas problems. So other oil and gas problems, definitely all the wells are connected, but in the shale case, is not so much. Yeah.
questions? I have a question. Nobody? Okay, there.
Hi. How do you think machine learning can help with the side effects of mining?
Side effects of mining?
Yes, because of contamination of waters and something like that.
Yeah, so, okay, I did not talk about mining today, but so in general, most of the work that we did and that we are showing here is related to the exploration side of predicting whether or not there is something in the Earth's subsurface. The kind of problem that you were saying is like, there are important problems of, how do you do the engineering of the facility in order to avoid something like that, or where do you put a mine in order to avoid the problem of doing that. And for example, in the case of Vale, they use like very old methods of mining that are not even used nowadays. So they use this kind of place to put the dejects from the mining and to do that, right? So this is not something within my area of expertise. What is being done, actually, IBM works with Vale is not the research side, but it's on the alert systems and things like that. But the political decision to put a mine in some place and to say, for example, build a cheaper kind of mine that you have to have this place to put the, so those are, yeah, we don't, fortunately, we have not worked on the green side of those areas, and I definitely would love to do some work on that as well. But since we are very focused on the geology, geoscience part, it's hard to go to the engineering part of it. It's a different kind of problem, right? The engineering is after the job. Like, all of this is very conceptual. I would go and drill here. It's not something like I'm doing how to drill. And one other thing, but mining, I think we cannot escape from doing mining also in the future, because all the materials that we need for all the things that we use, they come from mining. So some kind of geoscience, understanding where you can get resources is important, but it's good also that people start thinking of how to do things in a way that is not ruining the rest, right? The Earth is so big, there is like, we are only taking very, very small amounts from different things if you actually look at studies from mining specifically. And I don't think that is the biggest problem, to actually take the natural resource. I think the problem is how you deal with it, the engineering part that you mentioned.
Thank you.
Yes, more questions now? I have a question. So where is geology now? Is it at the point of doing tomography to know with enough resolution how much energy is going to be released and the impact on earthquakes?
This is like okay, so I don't work on the earthquake side of geology that I think you did, right?
Yeah,
so maybe you can answer that better than I did, that
was 10 years ago. So.
So if you want to say something about that. But no, I don't think geology has, or geophysics has evolved that much that we can predict earthquakes. If you want to say something,
no,
I'm curious. So
I have the state of the art like 10 years ago, so I wanted to know if...
Oh, okay.
Okay. Thank you very much.
Thanks.